Hello dear students, welcome to the physics classroom. This is gonna be an amazing session full of new learning. We want to continue explaining chapter number 5 entitled DC voltage. In this chapter, we will learn about an amazing instrument called oscilloscope. At the end of this video, you will be able to measure the voltage of a DC generator or a receiver using an oscilloscope, and also you will be able to read an oscillogram. Do you remember the role of the voltmeter? Here we have a short circuit made up of a lamp connected to a 4.5 volt battery. This battery has two poles, the positive pole and the negative pole. The voltmeter is connected across this lamp. It has two terminals, the COM terminal which is connected towards the negative pole of the dry cell and the V terminal which is connected towards the positive pole. So what is the role of the voltmeter? It measures the voltage between 2 points in the electric circuit. To which terminal of the lamp is the COM terminal of the voltmeter connected? As you see, the COM terminal is connected towards the negative terminal. To which terminal of the lamp is the V terminal of the voltmeter connected? The V terminal is connected towards the positive pole of the dry cell. How is the voltmeter connected to the lamp? As you see, they are connected in parallel. Now schematize the electric circuit of the lamp and the voltmeter. This is the schematic drawing. It is made up of the battery. This is the symbol of the battery. This is the positive pole, and the shorter one is called the negative pole. This is the symbol of the lamp, and this one is the voltmeter connected in parallel across the lamp. It has two terminals, the V terminal connected towards the positive pole and the COM terminal which is connected towards the negative pole, so that we can get a positive reading on the voltmeter. If the voltmeter allows us to measure the voltage across any electric component, do you know that there is an instrument that allows us to measure and also visualize the voltage over time? Yes, there is. This is the amazing instrument called the oscilloscope, which allows us to measure and visualize the electric voltage with time. But the question is, how is this voltage displayed on the screen of the oscilloscope? Let's first of all recognize some parts of the oscilloscope, and the beginning is with the screen. The screen is made up of a horizontal axis called the axis of time, where each horizontal square represents an amount of time, and a vertical axis which is called the axis of the voltage U, where every vertical square represents an amount of voltage. Each square is called a division. Its unit is diV. Every small dash is called a subdivision. It represents 0.2 divisions. Concerning this screen, the maximum number of the vertical divisions is 4 upwards and 4 downwards. There are 5 divisions to the left and 5 divisions to the right. To the right of the screen, we have a panel full of buttons. We will deal only with the basic buttons. This one is called the phase pole. This is called the ground pole. This one is called the time base. Its unit is millisecond per division. And this one is called the vertical sensitivity. Its unit is V per division. So this is the switch, the phase pole, the ground pole, the time base, and the vertical sensitivity. Now, how is the oscilloscope connected to the terminals of the generator? The phase terminal is connected to the positive pole of the dry cell, and the ground terminal is connected to the negative pole of the dry cell. So the rule says that the phase should be connected to the positive pole and the ground should be connected to the negative pole. But what if we reverse the connection? We will discover this later on. We said previously that the oscilloscope allows us to see the voltage on the screen. As you see here, we have a luminous horizontal line and this one is a luminous waveform. These two signals are called the oscillograms. So, the signal produced by the oscilloscope is called oscillogram. In your opinion, which one represents the constant voltage? I guess you say the first one, because it represents a constant line, unlike the second one which has so many ups and downs. In the absence of the voltage and when the sweeping is off, or when the VB button is adjusted on the zero level, a luminous spot is observed at the center of the screen. But when we sweep on the oscilloscope, the luminous spot starts to move on the x-axis and accelerates until it appears as a horizontal luminous line. So, when we sweep off the oscilloscope, a luminous spot is observed at the center of the screen. But when the sweeping is on, a horizontal luminous line is observed at the center of the screen. Now, in the presence of the voltage, when the sweeping is off, the luminous spot appears at the center of the screen. Now we connected the battery across the oscilloscope with the phase terminal connected towards the positive pole of the dry cell and the ground terminal towards the negative pole of the dry cell. The luminous spot moves upward. As we decrease the vertical sensitivity, this spot moves upwards more and more until it disappears when the vertical sensitivity decreases to 2 volt per division. So, in the presence of the voltage and when the sweeping is off and the connection is correct, a luminous spot makes an upward displacement. And as you notice that as SV decreases, the vertical displacement increases. Now, if we reverse the connection of the oscilloscope, the phase terminal is connected towards the negative pole of the dry cell and the ground terminal is connected towards the positive pole of the dry cell, we notice that the luminous spot moves downward and it starts to move downwards more and more as the SV decreases until it becomes unseen at 2 volt per division. So, when we sweep off the oscilloscope and the connection is reversed, a luminous spot makes a downward displacement. Now, in the presence of the voltage and when we sweep on the oscilloscope, the luminous spot moves rapidly on the x-axis until it appears as a horizontal luminous line. Now, when we connect the battery across the oscilloscope with the phase terminal across the positive pole and the ground terminal across the negative pole, the luminous line is drifted upwards and it starts to move upwards more and more as the SV decreases and it becomes unseen at 2 volts per division. So, when we sweep on the oscilloscope and the connection is correct, a luminous line makes an upward displacement. Now, when we reverse the connection with the phase terminal is connected towards the negative pole of the dry cell and the ground terminal is connected towards the positive pole, the luminous line starts to move downward and it moves downward more and more as the SV decreases and becomes unseen at 2 volt per division. So when we sweep on the oscilloscope and the connection is reversed, the luminous line makes a downward displacement. Now, how to make the schematic drawing of the oscilloscope? When the phase terminal is connected towards the positive pole of the dry cell and the ground terminal is connected towards the negative pole of the dry cell, we are measuring here UPN. UPN is related to U phase ground and the luminous line makes an upward displacement. But if we connect the ground towards the positive pole and the phase towards the negative pole, here we are measuring U and P and the luminous line makes a downward displacement. Now, how to calculate the voltage using the oscilloscope? Here we have different batteries connected to the oscilloscope such that the SV is equal to 2 volt per division. We have 3 batteries, battery A with voltage 2, battery B with voltage 4, and battery C with voltage 6. We obtained different oscillograms. All of these oscillograms are about horizontal luminous lines. The first horizontal luminous line is drifted upward by 1 division. The second horizontal luminous line is drifted upward by 2 divisions, and the third one is drifted upwards by 3 divisions. So the number of the vertical divisions, which is called Y, is 1 for the first battery, 2 for the second battery, and 3 for battery C. Now, if we want to divide the voltage by the number of the vertical divisions, we get 2 volt per division in each case. Now, how does the number of the vertical divisions, or Y, vary when the voltage of the battery varies? As you notice, when the voltage increases from 2 to 6 volt, the number of the vertical divisions, or Y, increases from 1 to 3 divisions. So we can say that the voltage is directly proportional to the number of the vertical divisions. Since the value of the voltage is directly proportional to Y, and since SV is equal to U over Y, we can get this formula. U equals SV times Y. The unit of U is volt, the unit for SV is volt per division, and the unit of Y is division. This is the general formula. Let's solve together application number 1. Calculate the value of the voltage. Given the vertical sensitivity, or SV, equals 2 volt per division. This vertical sensitivity, it means that each vertical division on the screen represents 2 volt. The luminous spot is moving upwards by 1 division, 2 division, 2.2, 2.4, and this is 2.5 divisions. So Y is equal to 2.5 divisions. By applying the general formula, we get U equals SV times Y. We substitute SV and Y by their numerical values, then we get U equal 5 volt. Now, we have to match the number of the vertical divisions, or Y, to their corresponding oscillograms. As we see here, this oscillogram is drifted upwards, or it makes a vertical displacement by 2 divisions. So Y here is equal to 2 divisions. The second line is drifted downwards by 1.2 divisions, but Y here is negative because the luminous line is below the axis of time. Concerning the third oscillogram, it is above the x-axis by 1, 2, 3, 3.2, 3.4 divisions. So the answer becomes this way. Now, let's solve application number 3. We have to calculate the value of U. This button is called the vertical sensitivity because its unit is V per division. So, SV is equal to 5 volt per division. The luminous line here is drifted downwards by 2 divisions. So, Y is equal to minus 2 divisions. By applying the rule, we get U equal SV times Y. When substituting SV and Y by their numerical values, we get U equal minus 10 volt. And finally comes the summing up. The oscilloscope is an instrument that allows us to measure and visualize the electric voltage with time. DC voltage is the voltage that does not change with time. Example, the voltage across the battery. The basic buttons of the oscilloscope are the switch, the phase pole, the ground pole, the time base, and the vertical sensitivity. The schematic drawing of the oscilloscope. This is the symbol of the phase. It is connected towards the positive pole. And this one is the symbol of the ground. It is connected towards the negative pole. And here we get a positive voltage. The calculation of the voltage, the rule is U equals SV times Y. So we get Y equals U over SV, and SV equals U over Y. Now, in the absence of the voltage, and when the sweeping is off, we get a luminous spot at the center of the screen. But when the sweeping is on, we get a horizontal luminous line at the center of the screen. Now, in the presence of the voltage, when the sweeping is off, the luminous spot is drifted upwards or downwards. But when the sweeping is on, we get a horizontal luminous line above the axis of time or below the axis of time. Now the question is, why does the luminous spot or the luminous line move below the axis of the screen? The answer is because the connection of the oscilloscope is reversed. It means that the phase is connected to the negative pole of the dry cell and the ground is connected to the positive pole, as in this one. Thanks for watching us and have a nice day.